no, this calculus concept is in fact not angry at you. The mean value theorem is kind of an interesting application of derivatives, allows us to make some interesting implications and inferences about a function given continuity and differentiability. So first, we're going to go over some past terms, differentiability and continuity. We're going to discuss what the mean value theorem is, and then we're kind of going to do some comparison and review to the intermediate value theorem, IVT, which we discussed a while ago. Right, so a reminder, continuity, which I'll abbreviate CONT, is kind of you remember the rough smoothness of a function. Continuity has its definitions. Remember, like, f of c must exist, it equals something, f of c exists, the limit as x approaches c of f of x exists, right? And then lastly, those two must kind of combine. F of c must be equal to the limit, limit x approaches c of f of x. Sorry, I'm kind of a disaster today. Must be all this mean calculus we're doing, right? So kind of a review back to the definition of continuity, right? Now, differentiability, which we briefly discussed a while ago, differentiability, which I'll abbreviate DIFF, it describes the existence of a function's derivative, right? So simply put, a function is differentiable if, so f of x is going to be differentiable if and only if both f of x is continuous and f prime of x exists, right? And both of these can be assumed for an interval, such like a to b, and these could be parentheses or brackets, inclusive or not inclusive of a. I guess I should say it's differentiable on the interval a to b, if and only if, right? Now, we should kind of discuss the one-way dependence of differentiability on continuity. Continuity does not imply differentiability, meaning you can have a continuous function that is not differentiable. For example, if you have a function that kind of looks like this, right? You're going to have a vertical tangent line here. And if you know something about vertical tangent line, your derivative isn't going to exist. Because if you think about what a derivative is, it's a value for slope. What is the slope of a vertical line? It's undefined. Your derivative doesn't exist where there's a vertical tangent. However, this function is still continuous. Right, so that's one example. You could also have kind of like a cusp or a sharp corner in your function. At these points, you're not going to have differentiability because if you think about those two-sided limits, the limit as you approach from the left and from the right, they're not going to be equal, and so you're not going to have a defined derivative going all the way back to the difference quotient, right? However, I'll rewrite this. Continuity does not imply differentiability. I forgot to cross that out last time. However, differentiability does imply continuity. Right. That is a condition of differentiability. For a function to be differentiable, it must be continuous. However, not all continuous functions and intervals are differentiable, right? And so that's important for the MVT, and you'll see why soon, right? Now, there is a third kind of definition that we could go over. It's not super important, but it's something useful to know. There's a function can be continuously differentiable or differentiable multiple times. Like if you've ever heard me say twice differentiable, thrice differentiable, that implies that your derivative is such continuous, possibly differentiable itself, right? You can take a derivative of a derivative. Again, a differentiable function doesn't always have to, the derivative has to exist everywhere. It doesn't always imply that there is a value, that there is continuity within your derivative. You very rarely run into a function that is differentiable, whose derivative is not continuous everywhere. Never with polynomial functions. You can get into some weird trig stuff, exponentials, fractions, rational functions, which may or may not have derivatives that are continuous However, we don't really need to worry about that for the MVT and for the sake of the level we are at now in calculus. However, the definition of continuity and the definition of differentiability are good to review for our mean value theorem. Right. Okay. Now we're going to kind of define the textbook definition of the MVT, recognize where it applies, what it is really, and then we're going to wrap this up. So if you skipped until here, the MVT, mean value theorem, as a broad textbook definition, let's say you have a function f of x. If f of x is continuous on closed interval a to b, meaning that it has to be continuous at a and b as well, right? And, keyword and there, both of these conditions have to be true. F of x is differentiable on the open interval a to b. Then there is a value, there is a value, input value c. We like to use c a lot, remember in our difference quotient, such that there's value c such that what's going to happen is the MVT guarantees a value, much how IVT guarantees, so we'll talk about that more later. The MVT guarantees that there is a slope value, a derivative value, equal to the average rate of change of the interval. Right? There's a c such that f prime of c is going to equal. Now, remember our average rate of change formula, the formula of a secant line, right? If you were to just kind of make a straight line between 2 points and calculate that slope, right? The slope of that line is going to be f of b minus f of a over b minus a, right? Kind of, this is your change in y over change in x, right? Delta y, this is a delta x. Now these are not dy values or dx values. dy and dx are infinitesimals. That's going to be what your derivative is related to. You can really relate this, or you really could say here, there's a value such that dy dx, given that x is equal to c, right? This is another way you can express derivative notation. This means the same thing as f prime of c. There is a c value such that your dy dx is equal to your delta y over delta x, right? And that's the special thing about the mean value theorem. It allows us to relate kind of a calculus version of a slope to an algebra form of slope, right? Algebra is something you might see more commonly in like physics of constant acceleration, stuff like that if you're into that, right? But the mean value theorem guarantees this, right? So what does this mean? Because this is kind of a lot of words. It might be difficult to understand at first. Let's draw a graph. I'm going to be over here. This is our function f of x. We're on the x-axis here in quadrant 1. Let us say we have a function that looks like this, right? Function exists at these points. This is going to be a, and over here I guess is we're going to have b. I didn't draw the axis out far enough. So this right here, our delta y over delta x, our average rate of change, the slope of our secant line is going to represent kind of this line here between points f of a and f of b, right? If you really think about this, f of b is this point, minus f of a, that's a change in y. B minus a is a change in x. So this is the slope of this line drawn here in red, right? Now, the MVT guarantees that there's a derivative value on this closed interval such that the slope of a tangent line made with that derivative will be equal to this secant line. And we can really see this here. Like I can kind of draw a line tangent to the graph right around here, and you see you're creating parallel lines, parallel between the tangent line and the secant line, right? The secant line being between those 2 points. Tangent line, we've gone over that in the past, right? So the MVT is really special. It's allowing us to kind of assume that our derivative is going to match this algebraic secant line here at some point, guaranteed, right? Now, you have to be careful, right? With the function here that maybe looks like this, kind of all wiggly, you can't necessarily guarantee that you'll have a secant line that equals your derivative at some point, because if you look, I try to roughly draw this function so that there would be a vertical tangent line here. When you have a vertical tangent line, your derivative no longer exists at that point, and so this function would not be differentiable necessarily everywhere, right? You're going to have a vertical tangent. So now we know where the MVT applies. MVT applies where you have continuity differentiability. Differentiability is the one you really have to pay attention to because most of the time we're dealing with continuous functions. Remember, calculus, study of continuous change. We care about things that are continuous, not so much about things that are not continuous. Differentiability, though, usually we'll have to check, especially considering this here, this special kind of condition, whether you have a bracket or a parenthesis here, right? Now, I like to think of this, if you're taking this in a class, right, as when you're taking derivatives, it's kind of an extra step, right? Things kind of get more complex, right? I like to think of, you have kind of like this sturdy basis here, continuity, you just brackets, right? But then as you kind of work on your function, parentheses, right? My brain's a bit weird though. It is important that your function is continuous on the closed interval. It cannot be continuous on an open interval. Let's think about what that would look like. If your function was continuous on an open interval, a to b, you could have holes in your function, in which we can't actually make any guarantees with the MVT, especially because these discontinuities here could be weird things like vertical asymptotes, right? We can't actually guarantee, even though it might seem like we can look at a function and kind of assume what the MVT guarantees, we can never guarantee that the slope of our secant line will equal our derivative at some point over an interval that is not continuous or continuous on an open interval, right? Discontinuities kind of throw a wrench in a lot of our assumptions and guarantees with these theorems here, right? Or you even think of like a jump discontinuity, right? You can have function maybe that looks like this, but then you have something like this. Where would you even draw your secant line? Well, you would draw it from where the points exist. If this is a closed dot, this is an open dot, draw it between the existing points, but you can't guarantee anything in an open interval. Cannot stress that enough. You need to assure that your function is continuous on the closed interval, right? Now, differentiability, it's not as important that you are differentiable on a closed interval, because remember, differentiability implies continuity, but continuity does not imply differentiability, right? You can have a function that has a vertical tangent line at a point, but then maybe kind of, you see what I mean here? So the most common example I can think of is similar to what I just drew, a function that kind of looks like sine, maybe not necessarily equal to sine, right? Or cosine. But you would have a vertical tangent here, maybe, and here at a and b, in which your function is continuous, but not differentiable, right? And so, but you can still make assumptions using the MVT, right? Now, I'm going to kind of compare MVT to the IVT, intermediate value theorem, a bit, because they are different, but for now we are done talking about the MVT. Oh, actually, we should talk about kind of a special case. I'm going to erase this kind of writing here. There's a special case of the MVT. It actually precedes the MVT called Rolle's theorem. I think that's how you pronounce his name, Rolle's theorem. It is R-O-L-L, Rolle's theorem, I think, Rolle's theorem. A special instance of the MVT where if, I'll draw a graph again, if f of a equals f of b, right? So they'd be on the same kind of y value. You could draw a straight line between them. then Rolle's theorem guarantees that your derivative must actually equal 0 somewhere, right? And if you were to think about this, if you were to draw a secant line between 2 points that lay on the same y kind of level, same output level, the secant line would have a slope of 0. 0 change in y over this change in x interval, right? And so Rolle's theorem makes sense as a special application of the MVT because you must have a spot where your derivative equals 0, right? And here in this case that I drew, it would be equal to 0 at that kind of peak, which brings me to my next point. With Rolle's theorem, if you recognize that f of a is equal to f of b, you can assume that there must be a peak or valley, a critical number. Remember talking about that a long time ago, right? And so if you're kind of ever reading a math problem, right, or looking at information of a function you're given, and you realize that there are 2 points in which the function is equal, the function output is equal for 2 different values of x, you can guarantee that between those 2 values, there must be an extrema, right? And so that's something that you can always look out for now that you understand how MVT works and Rolle's theorem, right? So now, let's go on kind of review IVT. We're done talking about new stuff today. We're going to compare. So the intermediate value theorem, if you remember, and I'll draw a third and final graph, is simply if your function is continuous on a closed interval, we must hit every single value between 2 points on a function, every single output value, right? Usually given by kind of a straight line. That's not the exact wording of the IVT. The exact wording of the IVT is, if a function is continuous and there is an f of c is between f of a and f of b, there is a value such that f of c is within there, right? You can guarantee that there's a value here. I'll just write it out like a continuous. These are the conditions for IVT, right? You have kind of f of a less than f of c less than f of b, right? You can guarantee that there is a c such that f of c exists, and that c is between a and b as well, right? Yes. So, but what you can really simplify the IVT down to is you're going to hit every single output value between 2 points, right? These values on the straight line here are values guaranteed to exist by the intermediate value theorem, right? And now with the MVT, we're talking about derivatives and slopes, right? So I'll draw a similar graph, kind of one like this. This would be kind of on some parabolic function, right? The MVT is going to guarantee that there is a derivative value equal to the secant line, right? Secant line going to be the same thing here for IVT. The IVT is going to guarantee every value, every function value on that secant line shows up somewhere on at least on one x input, right, between your 2 points. And the MVT guarantees that the slope of your secant line exists somewhere on your curve as a derivative, right? So IVT and MVT really are interesting ways to kind of make assumptions using secant lines, continuity, and differentiability, right? IVT with function values, MVT with derivative values, right? Now to sum up everything, as a little review, IVT only requires continuity, but the MVT requires continuity on a closed interval plus differentiability on an open interval, right? Oh, you know what? I forgot to put this on today. It's all this mean calculus we're doing. Anyways, see ya.